All right, good afternoon, everybody. So today I'll be going over my presentation, which acts as a progress meeting for the University of Manitoba's ongoing collaboration with Canadian Tire Corporation. My name is Kenneth Brzezinski, and I am the research intern lead on the project. Today we'll be going over some of my progress, some things I've worked on, some things I'm currently working on, and some sort of future projections for what I hope to accomplish in the 2 years left of our ongoing collaboration. So the overarching scope of this work is the identification of polymorphic malware using fractal complexity analysis. So presentation overview, as I said, is completed work within the first, since the 1 year since we've started our own ongoing collaboration, some current work and things that are in progress, and future work. So as a quick overview, this is doing a bit of a summary from my first presentation done in October of last year. A lot of my work is, I split it into two steps, and these are encompassed in two toolboxes. The first being the Sandy toolbox, and the second being complexity toolbox. So what these toolboxes are is they sort of facilitate the whole process of malware analysis from feature collection to model classification. So in this illustration on the right, for each of those yellow diamond box, we have the three core steps. So that'd be data collection, feature extraction, model classification. The Sandy toolbox is encompassed within this whole purple dashed box, and what it does is it handles any sort of work done in terms of feature collection, that is to execute malware samples and collect the relevant features and carry out the behavior analysis. Obfuscation adversarial is the act of introducing obfuscation into existing malware binaries. Adversarial being once we have our developed models, we're sort of testing them against adversarial examples that attempt to fool them. And thirdly, the classification step, classification malware from benignware. Secondly, the complexity toolbox handles all the feature extraction. So it's one thing to collect features and collect as many features as you like, but it's another thing to look at which features are relevant towards classification. And if you have too many, you want to reduce the dimensionality of the features so that you're only getting those relevant features that are trained on. And those are encompassed in two steps, one being feature extraction, extracting useful features, and some of the novelty of our ongoing collaboration is the complexity analysis. So again, this is a summary of a slide that I had showed last year, which is feature collection and how the malware pipeline works within the Sandy environment. So Sandy Toolbox in its current iteration can handle two steps, one being graphing and creating feature columns. Graphing being just a visualization of the propagation of malware and the sub-processes and the parent-daughter relationships of the processes as malware is executed on a system. And secondly, being creating feature columns, which is to say, if we collect information about related to the file system or registry edits of the malware or benignware, how can we take those and create feature columns? That is to say, create a representation that our model can understand. And to be added are two steps, one being obfuscation and the pipeline. Obfuscation, again, being as part of the pipeline, we want to obfuscate those vanilla malware samples and then throw them into our Sandy our virtual environment where we can collect those useful features. And pipeline being, once we have everything set up, we want to automate the process of taking a seed virus, obfuscating, importing into the Sandy pipeline, and extracting feature columns as a pipeline. So this illustration on the right just shows some of the helper functions that are involved in taking some of the process logs from Procmon, which is short for process monitor, and a series of helper functions in MATLAB and Python, which imports it into the Sandy environment where we can perform graphing and feature extraction capabilities. In terms of the graphing aspect, this is an example of execution of the Artemis virus within the Sandy environment, within our virtual machine. So how a system, or how an executable typical propagates is once it's executed from the command line, it's given a unique process identifier, or PID. And when that process spawns a daughter process, it's given another unique process identifier, but it's also given a parent process identifier, which is the parent ID of the parent, which is the process ID of the parent. So in this way, we can sort of look and recursively given a malware sample that we execute on the computer, see how it propagates by following the process identifiers. So in the bottom right, what we have is we sort of build a graph um, uh, object of our environment, and we produce an edge list using two keywords, process identifier and parent process identifier. This is just to say, let's just create a edge and node list of all the parent ID and parent process ID and create that node framework. What create target does is that string that is shown at the bottom right is the unique MD5 hash for the Artemis virus. So because we're choosing to execute it, that's what it's named by default, what we do is we execute that from the command line. And what happens is what create target does is it does exactly what I said. It looks at that executable, which is the Artemis virus, and its parent identifier, and it looks at all the other processes it spawned by looking at recursively the parent process identifiers that belong to a parent. And then we assign labels, which is just to say the nodes are by default labeled as their process identifier numbers. So we just can name them as their process names. And you can see in the top right illustration, all the nodes are labeled with the names of the processes. So when we set in create target verbose equals true, what we can see is we can see a little bit of a textual information related to how many target entries it found, unique process identifiers for the chosen target. It shows that there's one at 8168 and the second one being 2936. And it looks at those process identifiers and the process names associated with them. So the parent, of course, is the MD5 hash, because that's what we set as a create target. But it also found another process called file 2640385 underscore exe, which maybe is not necessarily an executable, but it put it in its name potentially to obfuscate. But those are two that were found by recursively going through the node framework and recursively finding spawn processes of the parent. And in the top right, we can actually plot based on color what is a target and what's not. And also in the top right figure, you can see the edges between the nodes are of different widths. And what that corresponds to is you can set it within the Sandy environment that the widths correspond to the time at which they were spawned. So it actually gives a time dimension to the figure, where the bolded ones occurred more recently and the thinner lines occurred later on. So in terms of feature collection, we've imported everything into the Sandy environment. We've produced our network of nodes and edges, and what we can do is we can look at all the unique operations of the processes that occurred. So in this case, just as an example, this is only looking at file system activity. So once all that information is imported in the Sandy toolbox, we can look at unique operations by using dot notation for operation and unique. And what unique does is it says, let's look at all the operations and just find the unique ones and return those as strings. So what create file does is it records all the creation of opening of a file, a directory, a disk, and any sorts of volume. So these are all the unique operations associated with file system activity. You're reading a file, you're querying, you're closing a file, and all these other sort of operations. So in the sandy.pp, being preprocessing import extraction, what the extraction method does is it will actually look at all the operations, again, these unique operations, and each of these operations has unique attributes associated with them. So as an example, once we do that and we pass in the command _info, it'll say, so in this example, test is set to true, and model.extract. And what that is just for testing purposes, it'll just extract the features from create file as default, but natively it'll actually go through the list and extract all the features for us and create a sparse data set of all these operations. Each of these operations, each of them having unique attributes associated with them. So in this example, we're just focused on create file, and then we can pass in the method or use the create._zip method just to create a zip file so that we don't have to do it later on, because that's very time consuming. So what model.info is doing is it's looking at all the features extracted from create file, and takes those raw attributes. So in the bottom right, we can see that it returned 2,466 unique entries, meaning out of all the processes that were run during the time we were looking at malware execution, there's 2,466 that we're creating a file, the operation create file. And then in create file, there's series of attributes associated with that. So desired access is I think a Boolean, or it could be, I can't quite remember that, but that may be a string that just looks at permissions. Things like allocation size is just a matter of how much size was allocated for the volume or the file to be created in disk. So each of these are a combination of integer values, floats, strings, and other types of category and ordinal values. So create file in particular, it returns a handle which has 8 attributes, and you can take a look at the Windows API online to see exactly what it's returning there. So going into the next step, we had looked at feature collection and feature extraction and its basics forms. Now we're looking at more of the complexity toolbox and what that offers us. And a big focus of our work is feature reduction. That is to say, it's one thing to take a look at all the unique features that we can gather, but what are the unique features that lead us to finding unique features that correspond to malicious behavior? Because it may be the case that there is not a clear decision boundary between file system activity of benign-ware and file system activity of malware. It's not clear that there's a boundary. So we need to find which features are relevant. And one thing we do is that's a work in of itself is reducing the dimensionality of the problem. That is to say, we're not considering a million different features of a sparse data set. We're only considering the 100 most relevant. Secondly, lower dimensionality leads to lower training time. If we have a million features, it takes a lot of time to distinguish and determine which features are relevant to malware and which ones aren't, right? So one of the things we can do as a preliminary step is take those a million features and either compress them into 100 or find a way to disregard 99% of them so that when we're training our model, we have lower training time. Also, it leads to faster runtime inference. So whenever you're training a model, each of those features has a unique weight associated with for how important it is to when making the inference to benign-ware or malware. So faster runtime inference means when we're actually executing, we want it to be quick, right? So we only want to consider those useful features when performing the classification. And better generalization is very important because the issue of dimensionality becomes a problem where your model has poor generalization when it's looking at too many features at once. You want it to generalize better by only looking at the most pertinent features. So generalizations is very important. And thirdly, genetic algorithms facilitate the search for optimal solutions in higher space. So a lot of our work carried out in the past year, shown in these figures as just a quick illustration for what this might look like, is a series of combinatorial optimization problems and global optimization problems where in n dimensions, we have too many parameters to tune. In the context of malware, we have too many features to consider, which ones are relevant and which ones aren't. So a lot of the work carried out in the past year was looking at what are better ways to find optimal solutions in very high order solution space. Because we can't take a million dimensions and try every single one, right? It quickly exceeds polynomial time in terms of runtime complexity. So what we want to do is we want to search in space what's relevant and what's not. And genetic algorithms have allowed us to do this, and we showed with a series of papers that we're able to do that. Again, searching in a solution space and finding optimal arrangements of features or optimal choices of features over others. So that was feature extraction or feature reduction. So we go more into complexity measures, which is a big focus of our ongoing collaboration and a novelty we add to our work. So feature extraction is concerned with extracting the salient features, those really important features from malware. And we do this based on this property of self-similarity. And self-similarity means that when you look at an object, it carries with itself the idea of self-similarity, meaning if you look at something at different scales, their same patterns emerge. And that's very important because we can use that as a measure to say, this malware binary or this series of network traffic, it has a certain complexity to it in its behavior, almost like a fingerprint. If I introduced malicious behavior, how would that complexity change? And if complexity is a useful measure, then it should be useful enough for us to be able to distinguish and classify benign versus malicious. So if you look at portable executive files, portable executive files have unique portable executive sections. So in the bottom left, you can see sort of these tall images, and above and below them are A, B, and C. So what A and B are A is a unique malware family, and those are two instances of the malware on the left and right. B is another malware family with unique instances on the left and right, and C just shows the general idea in a portable executive section where that would be on these images, very generally. So all I want you to take a look at is that it's somewhat clear to at least our eyes that A and B are very clearly two different types of malware. And again, these are just malware binaries. So these are just zeros and ones that are just used for illustration purposes, just plotted. But you can see that A, at the very bottom, it sort of has a different characteristic to how the portable executive looks. And the reason why is because these malware in particular, these malware families, introduce obfuscation. So you can belong to one malware family, but look slightly different. And that's very important. And B, for example, are two instances of the same malware family, but to our eyes, it is very difficult for us to discern that they're different. Right? They look the same. And in terms of our classifier, we want to classify certain malware families based on their structures, regardless if A, for example, the malware family has larger sections. You can sort of see black sections at the bottom. That's evident of garbage code insertion, or when the malware executes, it's adding garbage code to obfuscate and to fool signature-based malware detections that antiviruses are typically using, right? So we want to be able to our models to be sensitive enough to know that this malware is introducing garbage code insertion, but in not necessarily semantically, but structurally, based on what we've seen, they belong to the same family. So what we did was we had worked on a sample data set of 9,300 malware samples, and they were sourced from 25 obfuscated malware families. So 9,300 total samples, 25 separate families. And what we did was we developed a complexity-based model that incorporated complexity built into a convolutional neural network, with the most significant novelty of our work being the introduction of a vel max pooling layer, which actually performs box counting of the malware binary built into the convolution, and then we perform tensor summation and compute the complexity, and the backpropagation will backpropagate over the vel max pooling for us, because max pooling is typically used in convolutional neural networks. So we can form backpropagation through the network and then correspond certain weights and biases in the convolutional layer and tune those to perform our classification. So we were able to work out 96% plus categorical accuracy. And again, this is not binary accuracy where we're having two different samples. This is categorical accuracy. So it performed 96% on 25 families using a softmax layer. So that was our most recent completed work. This goes into more of the work that's in progress related to complexity measures, and this is focused more on time series. So our current work looking at complexity to predict the future of time series, with the notion that it's one thing to look at past history and past data to make future predictions, but if complexity is a useful enough feature on the behavior, we should be able to also look at the complexity of the information before us to make that prediction. And we show this, and I show this through a series of plots here, where the top row is complexity in time series, and the bottom row of images is just simply time series. And in the x-axis, we have different window sizes. These window sizes just correspond to, if I'm making a future prediction in the future of a point and what it's going to be, do I look at the last 3 points? Do I look at the last 5 points? Do I look at the last 7 points? Or do I look at the last 10 points in order to make that prediction? And what this shows very simply is that when you incorporate complexity in the time series, meaning at a window size of 3, it's going to look at the 3 last complexity measures as well as the last 3 points. So it's looking at the last 3 points and exactly where they are, but it's determining as in a form of a lambda layer. What it's doing is it's determining the fractal complexity of the previous points beforehand in the last stationary window, stacking that together and then making a prediction. And what this shows is that when you incorporate complexity built into the time series, it actually maintains that long-term dependency when it makes the future prediction. So in complexity and time series, the predicted follows very closely to the true, even with window sizes beyond 3 and 5. And the only reason why it gets worse is because these are not recurrent neural network. This model is not trained on a recurrent neural network. It's just based on a dense neural network. And dense neural networks don't have information related to its sequence, the sequence of data that's fed in. So it's just blindly looking at the last 3 points and saying, what is the future prediction? But when complexity is used, it actually acts as a recurrent neural network, while just looking at the time series again, which is just the last 5 or 7 points, well beyond a window size of 3, there's no information contained within those last 10 points that are used to predict the future. It's just not there. So this is a work that is a work in progress. So the preliminary results show that complexity can maintain that long-term dependency in order to make a future prediction in Brownian noise, which is what this information is. But the work needs to be validated on real-time series analysis, such as network traffic, because it's one thing to look at something that's stationary at every frame, like Brownian motion or Brownian noise, but it's another thing to look at network traffic, which is a dynamic, complexity changes over time. So that's something to look at. And one of the useful things of this, it can be used to create fake network traffic. So if we develop a model that is very sensitive to complexity and it's found to be useful, well, we want to be able to fool our classifier. And adversarial is one way that is used in image recognition. Let's just say to determine if someone's a person or a chair. Sometimes you can introduce simple images which throw off your model. So we want our model to be robust enough that we can create fake network traffic and our model with built-in complexity, because if our model incorporates complexity, our fake adversarial traffic should incorporate complexity as well, and see how robust our model is as a validation step. And in terms of producing our complexity traffic, one of the things that we hope to incorporate is an encoding and decoding layer. So this looks like a lot, but I'll work you through it. On the very left, we have X, which corresponds to a time series. The secondary X to the right just is the time series with complexity calculated. So here it just shows a straight line, but complexity changes over time when you're looking at a real time series. So what the encoding layer does is it looks at, in terms of a window, what it does is it looks at a set window size and it passes it through an LSTM cell, which is a long short-term memory cell. What it is it's a sort of a dense neural network that incorporates information about previous samples, and it carries itself a hidden state. So what these LSTM cells are doing, in fact, is it's taking each sequence of the time series and feeding into one another. So it's looking at contextual information that's passed in before and after. So this doesn't quite make a lot of intuitive sense for time series, but you can think of it in natural language processing. If I have a sentence such as I am blank to the store, it's very important that I look at the words I am in order to determine whether or not what that word should be, that blank word should be, right? I am blank. Could be I am, young. I am Ken. It could be a lot of things. But how LSTM cells work when they're set to configured bidirectionally is that they also look at the points before and they look at the points after in order to make that prediction. So if I go I am blank to the store, it knows that the word store is usually used in the context of traveling. And when you say I am, it usually means you are going to there, or I am leaving. So it learns that context based on the words around it. So the LSTM cells, when they incorporate bidirectionality, will look at the context of the points after in the window and the points before in the window to make that prediction. So that's how this is incorporated here. The reason why it's called an encoding layer is because it takes that information, takes the hidden representation, which is the these sort of latent variables that are created from one iteration to the next, and it flattens it and passes into a dense layer, which acts as a very dense representation of what that contextual information is. And this decoding layer on the right is a series of, again, LSTM cells that when you look at them, look at their hidden representations, what you can do is you can make future predictions based on that dense representation. So you can think of it as it takes all that information about the context of this in natural language processing of the sentence before it, the sentence after it, creates a dense representation of it, and sort of says, okay, here's this dense representation of it. Here's a new context. What are the potential words that will fit in my blank? So I am going to the store, I am traveling to the store, I am coming back from the store. Well, those are two words, but ideally you want to fit it with one word if you're making one prediction. In time series, the same sort of rules apply, except it's looking at the points before in the window, points after in the window, or the iteration before. It's also looking at the complexity before. Again, it makes sense contextually in natural language processing, but it doesn't make too much sense in time series. But the context of the complexity before and the context of the complexity after and how it's changing make a future prediction. And ideally, we hope this to be the first implementation of decoding and encoding and decoding for time series analysis by incorporating complexity. So one of our additional work is, again, it's very important to us is obfuscation, because 80% of all new malware samples that are realized every single day tend to be obfuscated in some way. So we want to introduce obfuscation to the Sandy pipeline directly. And two very popular virus generation kits are the NGV-CK, or Next Generation Virus Creation Kit, and something called the Virus Creation Lab 32-bit, VCL32. So those are some of the two most popular creation kits used in literature to this day. And how that works is you take a vanilla executable, it's disassembled in its ASM files in a software package such as IDAPRO, it's obfuscated, and then it has to be recompiled. And yeah, so everything has to be reconnected, recompiled back to an executable where it can be actually ran. So NGVGK has shown to create some of the highest rates of false negatives when antivirus software uses their signature-based techniques to flag them as anomalous or not. So it has a high rate of false negatives for antivirus vendors. So how sort of the pipeline would work is it takes a seed virus, it obfuscates it, we would send it to VirusTotal using their VirusTotal API, and it would see if which antivirus vendors and their signature-based techniques, which of them flag it and which of them don't, and then we'd import to the Sandy environment in order to look at all that dynamic behavior. So just as an illustration for how an obfuscation looks, here at the bottom in this table we have a series of assembly instructions before obfuscation, after two different versions of obfuscation. So on the very left we have just what a seed virus would look like, where it's calling a function A, it's populating an EBP registry, and it's substituting from the EBP registry and then offsetting function A. So it can be obfuscated where it's semantically similar to before obfuscation, but some of the instructions are either reversed or they use different registries, or the instructions are substituted where it semantically has the same instructions. So it performs the same operation, runs normally, but it looks differently. And the size of for example, the binary would be different as well, right? So it's not enough to look at the size of a malicious binary from one iteration to next to know if it's malicious. You actually have to look at how its behavior is, which is what we do in this, how it's incorporated in the Sandy toolbox. And on the very right, we have a second version of obfuscation where it looks almost totally different from before obfuscation, but you can see that it's using registry reassignment, just changing registry names. It's introducing a series of junk, where a junk is just inserted in a certain section of the assembly instructions, but either a jump statement directly jumps over it and never executes, so it looks like the file is bigger than it's not, or that junk code insertion could perform an operation like add to a registry and then substitute the same value from a registry, in effect doing no work. But just by adding those assembly instructions, it's introducing obfuscation. And one of the biggest forms of obfuscation is instruction substitution, where you take one instruction and then you can replace it by a semantically similar set of instructions that are 2, 3, 5 instructions long. So it makes things look more complicated, but in effect, it's either performing an operation and reversing it, or it's jumping over a series of instructions and never executing it, thus making something that looks simple, like a totally different set of assembly instructions, performing a totally different function, but in effect, it's the same, it's semantically similar. And from some of our future work is the form of classification. So in our recent work, when we're working with the malware binaries and the complexity convolutional neural network, we looked at a series of different models to see whether one was more beneficial than the other. And when it comes to different types of classification, it's very dependent on the features that you're given. There's no one-size-fits-all. But one of the benefits of unsupervised models, such as k-means, is that it learns based on proximity of feature vectors. So what that in effect is saying is, if I have behavior over time of benignware, whatever those features are, it tends to cluster in some place in vector space. Okay, so it clusters together in whatever that dimension of vector space is. But if my features are salient enough, and let's just say I'm using complexity analysis, if I introduce malicious behavior, it'll have a different sort of representation in vector space, and it'll be in a different position. If we're talking about position based on some sort of distance metric in the solution space, and ideally in an unsupervised model, if your features are relevant enough, the benignware and the malware will form different clusters. And just based on that difference in clusters, we can say, hey, this behavior is not like the rest. Therefore, we should stop that behavior. It's anomalous. But it requires very good separability between features. And how we're using the sandbox now is that we can actually execute the malware samples and track everything. So it's all being labeled as a supervised our models are supervised classifiers, as they are now. And as I said, supervised models are still effective for distinguishing obfuscated malware. There's no one size fit all. Not necessarily saying one works better than the other, but how malware is in the future is that we'll get new samples and we don't necessarily know, because they're obfuscated. It's not something we've ever seen before. So potentially unsupervised model where we're separating, again in vector space, may be useful to us. And this slide just goes to show, as a student and my progress so far, having finished 1 year of this project, where I am in terms of coursework, having finished all my completed coursework in my first year. In terms of the Canadian Tire Corporation and my 3-year internship, I'm finished my first year of the 3-year commitment. And in terms of publication, we've published 2 works on feature extraction, but feature reduction related to a hybrid particle swarm optimization, our particle swarm optimization techniques. We also published a paper related to adaptive particle swarm optimization that's in the press, and we've published and it's been accepted our malware convolutional neural network classifier. And 2 of the works in progress is the book chapter related to obfuscation, shown in about 2 slides ago. And our malware recurrent network is a work in progress, and that's a big work in itself. And the Sandia toolbox is something that, as a pipeline, has not actually been published yet. So that's a paper that we hope to work on in the future. And undetermined papers, it takes about 6 months for me to look back and say, what do I have going forward? Things change, and sometimes these techniques don't always work out. So it's hard to say what is to be worked on, even 6 months from now, because things just change. So in terms of graduation, I finished my first progress meeting. My PhD proposal is actually not complete. It's still something I'm working on. And I have things like my candidacy exam, my second progress meeting, and of course my thesis to be concerned about. So with that, that's the end of my presentation. You are more than welcome to send me direct messages to my email address, any questions about things that I've done, any clarifications on the paper that I've published, and again, any sort of clarification related to this presentation. Send it to my email and I'll get back to you as soon as I can. And with that, I'll take thank you for your time.